Apologize if you're just watching the recording. I've got questions up on the board that I've given the students time to do. We are going to discuss each of them in just 1 minute. And I'm going to say time's up. This is giving me a chance to see and understand a little bit. So let's go over each one of these. The correct answer for A is yes. Magnets have north poles and they have south poles. They have a north side and a south side. Every magnet has a north and a south. And if you have two magnets, which I strongly encourage you, if you have never played with magnets before, the lab room has magnets in the supply closet. Ask your lab instructor. If you have two magnets and you try to push the north together with the north, or if you try to push the south together with the south, you will find that they repel each other. If you allow the north to approach the south, or the south to approach the north, you will find that they attract each other. So, big principle of magnetism. Opposites attract, like repel. Not charges. I do wish to emphasize very importantly, there is nothing plus about north, there is nothing minus about south. These are not electrical charges. As it happens, there is a deep connection between electricity and magnetism, but electric charge is not magnetic polarity. Every magnet has both a north and a south. Every magnet has both a north and a south. Every magnet has both a north and a south. If you break apart, if you take a drill, a saw, and cut apart the north side of a magnet and a south side of a magnet, you will end up with two magnets. One of them will have a north and a south. The other will have a north and a south. It is impossible to break the north off from the south. We fought a war about that. Thank you. You too, good days. It's impossible to break the north pole off from a south pole of magnet. Yeah. No, do not refer to them as positive and negative. They are not the same thing as positive and negative. If I say you have got positive, I'm thinking about a charge, a proton. If I am talking about a north, I am talking about a pole of a magnet. Now, we can talk about a numerical quantity, the magnetic field, which can point, for instance, north or south or wherever. And the magnetic field we can assign a number to. You could absolutely say that the magnetic field of Earth is 52 microtesla pointing north. That's a true thing. And so if you turn a magnetometer, a meter which measures magnetic field, backwards, it would indeed say negative 52 microtesla. That does not mean that I have found negative magnetism. Magnetic poles are still north and south, but it tells me the push or pull on a compass. I don't want to get deep into what Tesla is. I don't want to get deep into the understanding how Teslas are defined, the unit of magnetic field. But let me say that the push or pull on a compass would be in the opposite direction you're currently measuring. You're not measuring a negative magnetism. The only place where you would have a plus or a minus sign in magnetism is you would associate a measurement of the magnetic field, which we are not really emphasizing yet. We'll do that more in the second module. We could associate that with a number. We're not doing that yet. So what I want you to know for now is that magnets have north sides and south sides. And you should also know that opposites attract with magnets. And light, therefore, repel. So, is there a north side of a magnet? Yes, always. There's also always a south side of a magnet. Part two, which side of a magnet? I think the student was asking about a compass in particular. Compasses are magnets. That's also an important thing to know that I did not explicitly necessarily state. Which side of a compass, which pole of the compass gets pulled up towards Alaska and the Arctic Circle? The North Pole is defined as the side which is attracted to the north side of the map. The north pole of a compass is defined, the north pole of a magnet, any magnet, is defined as that which is attracted towards Alaska. Okay? Now, question C discusses, does north face south? No, north faces north, south faces south. North part of a compass, we define the north side of a compass by whether it faces north. So part C, does this mean the red part of the compass is actually the south part? No, the red part of the compass that has a big N on it, N stands for north, and that actually means it's the north side of the compass. The north side of the compass is attracted to an opposite magnetic pole, which means that the Earth is basically a big freaking magnet itself, which is flipped backwards from what you would expect. The Earth's magnet, the magnet that is the Earth, has a south magnetic pole up in the Arctic Ocean and a north magnetic pole down in Antarctica. That is to say, the top of the map is south, pole, magnetic pole, and the bottom of the map is a north magnetic pole. That's why the red side of the compass points towards the Arctic Ocean. It points up along the map. Because opposites attract, and sitting up there in the Arctic Circle is a south side of a magnet, a really honkin' big planet scale magnet. That's what attracts the red side of the compass, which is marked N, which is the north pole of the compass magnet in that direction. Now that has been proven rather confusing to a lot of people, that opposites attract means that the north side of a compass is attracted towards the south side of a planet, which is actually in the Arctic Circle. That has confused a lot of people. Please turn to your neighbor and discuss this for half of a second. Wait, hold on. I have a question before that. Please, everyone listen.
It's attracted
The north side of the compass is attracted to the geographic north. The north side of the compass points towards Alaska, Canada, Greenland, Arctic Ocean. That's the north side of the map. The north side of the compass is defined as that which points that way.
You're just missing geographic. I think you meant geographic poles.
Yeah.
So the north side of the compass is not attracted down. The north side of the compass is attracted towards the top of the Earth.
Like south, you're saying south of the magnetic.
And you know what? Maybe a graphic show is worth a million words. Let's draw it. Here is the Earth. Here is Antarctica. Here is Canada. You are here. Okay? If you hold up a compass, the compass points. Its north side is traditionally colored red. The compass points. North is that way, towards Canada. I mean, duh, right? If you've ever seen a compass, you may note that the north side of the compass does indeed point north. That is how we define the north side of a magnet, of a compass. Now, again, maybe this will work better with pictures here. What attracts a north side of a compass? A south magnet pole. That is therefore equivalent to the entire Earth is equivalent to having a big south side on top and north side on bottom. The Earth is equivalent to having a big honkin' magnet with the north magnetic pole down south and a south magnetic pole in geographic north. Again, this doesn't mean that the south side of a compass is secretly north. It means the south side of the Earth has northern magnetism, if you will. And the north side of the Earth has equivalent of a southern magnetic pole. And then inside the Earth, things get crazy. Well, beyond the scope of this course. North is pulled south. North side of a compass is pulled towards a magnetic south pole. Yes, exactly. The north side of a compass does indeed point towards Canada, right? North points north. Yes, that's what I mean by north side of a compass. The end that is pulled towards Canada. So what's in Canada? If Canada had the equivalent of a big honkin' North Pole, the north side of the compass would have to point away from it. Canada has to have the equivalent of a big honkin' south magnet up there. South side of a big planet-sized magnet. Yeah. The magnetic field of the Earth, that is, if the Earth were replaced by a big, big magnet, that's how it would have to be. Upside down. Okay, again, turn to your neighbor and discuss. I would like everyone to be able to answer which side of the Earth has a magnetic north and which side of the Earth has a magnetic south. Ready, set, go. Take 1 minute. The geographic south has a magnetic north. So the north side of the magnet is always attracted to south sides of magnets. And if the north side of the magnet is attracted towards Canada, Canada is the south side of the magnet. Effectively. No, geographic means if you hold a map, north is up. Geographic is this is north, this is south. Geographic north is the end of a map. Geographic north is not attracted to anything. If I have a magnet, a compass needle, the north side of the compass needle is attracted to the north geographic pole. Yeah. And what attracts north sides of compasses? South magnets. Yeah, south parts of magnets. Okay. Question me. You may realize after you turn to your neighbor and discuss that you have a further follow-up. Please. Mm-hmm.
This one was going to be the behavior.
Sure.
Clockwise or counterclockwise or either.
Sure.
Why didn't go counterclockwise?
I will do my best to open that up. I've got it open for another problem. Do you remember which number that was? Great. I will do my best to get to that. Let's go down through the rest of these, though, while we're at it. Okay. So I encourage you, by the way, always write the letters in the same order. I quizzed people, do they remember the force formula at the end of last class? And there were a lot of QVBs, there were a lot of QBVs, there were a lot of QVVs, there were a lot of QBVs. I think I said the same thing. There were a lot of permutations of it. I encourage you, the letter V comes before the letter B, so put it, oh, wait, it doesn't. But you can pretend it does. When I write the formula, I always write QVB. First V, velocity, then B, magnetic field. And I write that because it helps remind me what order to do the fingers in. Okay? The velocity finger comes first because V comes before B in the formula. V cross B. First your fingers. If I say point in the direction of blank, wouldn't you use your fingers to point that way? Yeah? If I say point to the right, wouldn't you guys point to that direction? If I said point down, wouldn't you point with your fingers down? So your fingers are the first direction because that's what you normally point with. Someone says point down, then palm over. You're pointing with your fingers. The second vector, the second quantity with a direction is magnetic field, B. V cross B. So then I rotate the next oriented part of my body, which is the palm, in that direction. I want to emphasize, by the way, if you're still getting these wrong, the most common goof that I see is people will point, say, up with their fingers, and then they hear point to the right of the room, and then they instinctively move their hand so that, oh, but their fingers are pointing to the right of the room. No, 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 no. Your fingers are the first direction, and if your first direction is up, your first direction does not then change. Your finger direction cannot change. So if I say up, cross, right, leave your fingers up. Do not turn your fingers. Okay? What you're allowed to do is rotate your wrist, or you can move your arm around if you need to, but you've got to keep, if your first vector is up, your fingers are up, the velocity vector is up, the particle is moving in the upward direction. Your fingers have to point upward at the end of the problem. Check yourself with this. Hey, by the way, what is up, cross, right? Everyone show me your right hand and do it. Do it. Up, cross, right. Up, cross, right. Up is the first direction. Right is the second direction. I think that is into the page. Good. You caught yourself. And the direction your hand should be in. Your hand should be parallel. Your hand should be parallel to mine right now, wherever you're sitting in the room. Make sure you're using your right hand. And your palm is facing the opposite direction. Face that side of the room. Palm faces that side of the room. You're giving someone a high five over there. There you go. That is right. Your right side is that direction, yeah? So you want your second direction, your palm direction, to go that way. There is if the palm, let me just ask, by the way. If no one is confused by which direction your palm faces, then I'll skip it. Is anyone having trouble remembering or figuring out or thinking about which way does your palm face? You all comfortable with your palm facing that away? Great, okay. I'll take it. Okay, so the correct answer is, how do the fingers and palm relate to V and B? Fingers V, palm B. And thumb is the result of V cross B, V times B. Don't forget, I totally reserve the right to give a question where a negative electric charge is feeling a force. V cross B itself does not change. Calculate V cross B. If Q is positive, I would say positive number times right is right, for instance. But if I have a negative charge, negative times right would give the left direction. Negative right is left, negative up is down, negative blah is blah. The force formula, if you don't know what I'm talking about. QV cross B. First I calculate V cross B with the right hand rule. If Q is negative, negative left is right, negative up is down, negative north is south, whatever. Flip it if it's a negative charge feeling that. Okay. Incidentally, this might be a good problem, good time to switch to Steven Universe. No, to switch to a problem that was given on the test, given on the homework. I had a question about a particle is circulating. Oh, we talked about circular motion last class. Last class? On Wednesday, right? Yesterday class? If we have a particle which is orbiting, turning in this direction, here's how I would analyze this. Which direction is the force on the charged particle in order to turn in a circle? What do you always know about forces on things moving in circles? The direction is inward. You have to exert a force inward to push the velocity, which would go straight, into a circle. From last semester, centripetal acceleration, centripetal force, the direction you have to turn. If you're doing a right-hand donut, you are not pressing the gas, you are not pressing the brakes, you are turning the steering wheel in order to turn the path of your car. You are getting a force to push at right angles to your motion. So here's how I would analyze this. I've got magnetic field pointing in. Which finger's that? Well, the palm. Which side of the hand? The magnetic field is the palm. Let's pick any point along this, say the top. At the top of this circle, which direction is the velocity of the particle? I think if I'm looking at the particle when it's on the top of the path, the little arrow is showing me that the direction of motion is to the right. That's what that arrow is showing me. If it's going around this direction at this moment, this is the direction of motion. Okay, so let's look. Is this velocity cross this magnetic field in to the center of the particle? I'm going to put my first fingers in the V direction at this instant, my second fingers at the B direction at this instant, right? Which direction is the force on a positive particle? Which direction is V cross B? Is that pointing towards the center? No. I want force to point inward. So if V cross B is up and I want force to be down, what must the charge be? Negative. Merry Christmas, there's a homework problem. Question. So,
Indicating that B is for the axis, correct?
yes, also you can see if it says the magnetic field is directed into the screen, and I draw a whole bunch of into the screen directions, that's what I'm talking about. What is going up? Be precise. What is going up? The velocity of the particle, the force? Go on. Must.
Push it down. So, okay. Yeah.
Q has to be negative because V cross B, at this instant, V cross B points up. You could do it at any place along the circle, by the way. If I do it over here, I'll find it's to the right. If I do it down here, I'll say that it's down. V cross B at any point on this circle, V cross B is pointing out. So if I want force to point in and V cross B points out, I must have negative Q. Sure. Did you have a question? I saw there was someone else who had a hand up. No? Okay. No. I wanted to hit the rest of these and then we'll go back to number 5. Okay. How do voltmeters behave? Well, first off, what do voltmeters measure? It's right there in the name. I hope you got that voltmeters measure voltage. And a very important principle about voltmeters is if you allow electricity to flow through a voltmeter, that will disrupt the voltages and currents and the electricity in the circuit. Voltmeters are designed to block any current through them. Voltmeters are equivalently infinite, 100 million ohms resistance. Current must not be allowed to flow through a voltmeter. Voltmeters have high resistance. So a voltmeter is always placed in parallel with something you want to know the voltage across. Why is it in parallel? What's true about voltages in parallel? Basic principle about voltages and parallel. Parallel voltages are always identical. If you place a voltmeter in series, it will royally screw everything up. It'll stop any current flowing through that part of the circuit. Oh no! Actually, we could do a problem with that in a little bit if we have time. If you place a voltmeter in series, it will screw up. The circuit will no longer behave like it was behaving. You won't be measuring the voltage you think you're measuring. So facts to know about voltmeters. How does a voltmeter behave? It measures voltage, duh. You always place it in parallel. It always has high, very high, effectively infinite internal resistance. Ammeters. An ammeter is not an ohm meter. Ammeter measures amps. Amps are current. I had a bunch of people tell me ammeters measure resistance. No, that's an ohm meter. Ohms are resistance. Amps, ammeters are current meters. So what does an ammeter do? An ammeter measures current flow. And as you hopefully should not be too surprised to hear, if you want to measure current, you shouldn't block that current. If you want a current to flow through a meter and you want to find out how much current is going through that meter, it doesn't make any sense to block that current going through the meter. You want the current to flow through the meter just like it was flowing through the wire. So that's what an ammeter is. It's a wire inside, sort of. Not really, but kind of. I'm only slightly lying to you. An ammeter has low internal resistance. And if you want to put it in a place to measure an identical current to something, how do you get identical currents? Identical currents happen in series. Exactly. Ammeters, series, low resistance, currents. These things go together. There's also things called ohm meters. You use them in lab, most of you. We're not dealing with them. I will not put them on the test. They're useful little devices for measuring resistors, but I want to focus on just a couple things well, rather than everything there. Again, I strongly encourage you, if you think about the nature of what voltage and current mean, you don't have to wonder, or you don't have to memorize. If you have a resilient, a robust understanding of the meaning of current, it should be bleedingly obvious Once that clicks, it should be bleedingly obvious. Well, of course you can't block the current if you're trying to measure a current. Emitters have to have low series resistance. What is a switch? A switch is a piece of wire that can move. That's it. That's what the schematic symbol looks like. That's what goes on inside a switch. It is just a piece of metal that is movable by your hand. When I have an open switch, an off switch, a disconnected switch, a switch turned to the off position, all keywords, that says that the metal is not connected on both sides. If I have a switch turned on, closed, short, these are words to say that the metal is connecting the metal on either side. What is short? What does the word short mean other than your face is short? Okay. It's funnier for my high school students. So a short circuit means that the 2 points are connected. A short circuit in particular, what we actually use this in practice is a short circuit is where 2 points that you don't want connected to be connected. If I short out a component, I am attaching a wire path from its beginning to its end. So nothing's going to flow through that. It'll prefer to go through the wire. The opposite of short, by the way, do you guys know opposite of short? It's not a tall circuit, it's a open. An open circuit. If I've got an open circuit, that means disconnected. Like I just said about the switch terms, if I've got an open switch, an open means disconnected, just hanging out there with a gap. Yes, that is short. That is a closed, that is an on switch. Exactly. No, no, you want a short connection from the power wall into your circuit. If you want electricity to flow in, you need a connection there. Short does not mean bad. Now, suppose you attach a switch to either terminal of a battery. If you turn the switch on, then all of the electricity is going to short through the switch and discharge your battery. The circles are just a guide to guide the eye so you can see. And sometimes they don't even appear. I don't think on my graphics in my library, I don't think they even appear. Sure. And we have time. Let's do it. Let's do a voltmeter example. Here, I'm going to give you some right and some wrong circuits, and I want you to explore what happens. Explore, analyze with each other. I have a 12-volt battery. I have a 4-ohm resistor. I have not another 4-ohm, how about an 8-ohm resistor? There we go, adds up to 12 just for the hell of it. I'm going to connect a voltmeter. No, I want to put it elsewhere. And I'm going to connect an ammeter too. An ammeter is in series, a voltmeter is in parallel with a component. I challenge you to find the readings on these meters. What have we got up to, I and J? Here, I is find what does this ammeter say. J is find what does this voltmeter say. Now, incidentally, this is the wrong way to hook it up. I don't want to put it there, actually. I think I'll move things around. And I think I'll just put one. Okay, so your challenge is whether or not you choose to accept it. Google question I in the top circuit, find what you think that ammeter will read. Google question J, tell me what you think that voltmeter will read. And Google question K, can you figure out what that voltmeter will read? You can really think through these, you'll have learned something. Take a few minutes, and I encourage you, as I always do, turn to your neighbor and discuss these, and you'll learn more out of it. Learn from each other. The answers may surprise you. Not being clickbait or anything, but What a-
It's pretty soft for ammeter because it's connected in series, so it has to go through this part and here.
That's correct.
So you would find the total resistance and the total,
Exactly.
and the voltmeter is just for this part.
So how much current flows through that 4 ohms?
One, because it's in series, the current would be the
Oh, I
same.
see. That looked like 1.4. Yes, that's correct.
Oh,
Good.
okay.
You got it. Those are the first two.
Okay.
Good job. Let's see how many people have got through there. Okay, 1 minute left. Okay, time's up. So, I encourage you, if you know what we just said, that an ammeter has basically zero internal resistance, it's just a wire inside, sort of. And a voltmeter is basically an infinite ohm resistor, no current flows through it. You could ignore, you don't have to draw something. If I'm just analyzing how does the electricity flow, it might be useful to redraw this with the ammeter replaced by a wire and the voltmeter replaced by an open circuit. Well, you don't need to draw it if nothing flows through it. Do you know how to analyze this circuit? I hope so. How do we analyze every two resistor circuit? We add their resistance using the appropriate formula and find the current that leaves them. What is the equivalent resistance of a 4 in series with an 8? 12, that's right. How much current leaves a 12-volt battery if it were connected to a 12-ohm resistor? 1 amp leaves the battery. How much current flows through the 4-ohm resistor when 1 amp leaves the battery? How much current flows into the 4-ohm resistor if 1 amp leaves the battery? Google form! 1 amp of current leaves this battery. How much current manages to get into the 4-ohm resistor? Google form L. One more time. The question is, if 1 amp of current leaves the 12-volt battery, how much current enters the 4-ohm resistor? How much of that amp enters the 4-ohm resistor? Oh, okay, we need to review this. Okay, the correct answer, write this down. That resistor is in series with the battery. You must know, in series, current does not change. If 1 amp leaves the battery, 1 amp flows through that top resistor. 1 amp leaves that 4-ohm resistor. 1 amp enters the 8-ohm resistor. 1 amp leaves the 8-ohm resistor. 1 amp flows back up into the bottom of the battery. Series circuit, current is always the same. 1 amp is 1 amp is 1 amp, baby. If this were parallel, then we could split up. But it's not. Okay, so 1 amp leaves the battery. 1 amp flows into the 4-ohm resistor. How much voltage does the 4-ohm resistor lose? 4. The meaning of V equals I times R. The meaning of V equals I times R is if I have a resistor, how much voltage is lost by that resistor when current flows through it? Riddle me this, Batman. I start with 12 volts, I lose 4 volts. How much is left for that 8-ohm resistor? 8 volts. If I start with 12 and subtract 12 minus 4 volts, I'm left with 8 volts left. Okay, so in question J, in the correct answer for question J is 4 volts are burned in that 4-ohm resistor. Were you following along well enough so that if I change values, you could successfully still solve this? Question me.
So for J, what I was thinking it goes through A,
Be precise, what goes through A?
the voltage goes through A,
Voltage does not go places. Current goes places. Current goes through the ammeter, yes.
through A, but it goes around the 4 resistor and into the
But what did I just say at the beginning about how much current flows through a voltmeter? If that were an ammeter on the side, absolutely. If that were an ammeter, the ammeter behaves like a short circuit, behaves like just a wire. Why would any current go through 4 ohms of resistance when it could go through 0 ohms of ammeter? But it's not. It's a voltmeter. Did y'all hear his question, by the way? You should learn from each other. Yeah? Not just the what's right, but what's wrong, too. Okay, the other most common, half a second, Selena. The other most common goof I saw just now is that people took 12 divided by 4 is 3 amps. The meaning of V equals IR is not the voltage at the left end of the resistor equals the current through the resistor times the resistance of the resistor. There is 12 volts of voltage present at the top of this resistor. That's true. This point, if I wanted to assign this a voltage value, I would say that this point is at 12 volts. Yes, sure, okay, I believe it. By convention, I claim that the negative terminal of the battery is the 0 volt level. Big principle about series voltage. Series voltages add up. Series voltages add up. The voltage across the top resistor is somewhere between 12 and 0 because that resistor burns some of, but not all of, those 12 volts. What you could say is if I start with 12 volts of voltage, I lose some here, I lose the rest there. People are plugging in, many people, some people are still plugging in 12 volts divided by 4 ohms. It's not that the 4 ohm resistor is exposed to a certain amount of voltage, it's how does the voltage change across that. For instance, I don't know if you've ever noticed, but flying rats, aka pigeons, burbs, can in fact sit on power lines. Pigeons can sit on power lines. They can be exposed to voltages of hundreds of thousands of volts and high tension lines. Why do they not die? Why are they not Kentucky Fried Chicken up there? Kentucky Fried Pigeon up there? Because while one leg is at 100,000 volts, the other leg is at 100,000 volts. There is no voltage difference from one side to the other. If said pigeon had one leg on the power line and one leg on a grounded point, then you better believe there would be a nice smell in the air and lots of crispy chicken, pigeon falling on our heads. If there is a voltage difference from one side to the other of the resistor, that's what drives current. Just having 12 volts there does not mean that the 4 ohm resistor is pulling 12, has a voltage of 12 volts. The voltage across the resistor is whatever is on the subtract what is on one side minus what is on the other. In this case, how would you find this? Well, I would reason backwards. If I have discovered that 1 amp leaves the battery, I know the current and the voltage, current and the resistance. That's how I find the change in voltage. Okay, so the correct answer for for I was 1 amp. The correct answer for J was 4 volts. Now let's go on to the challenge K. Tell me this. What is the effective resistance of a voltmeter? Big! Do voltmeters like electricity to flow through them? No! They block up current so that they can keep from disrupting the circuit. What happens if you put a big resistor in series with these resistors? Will current flow? No! No electrical current flows because it is blocked by this effectively open circuit. Tell me this. There is no current passing through this 4 ohm resistor. What's the voltage here? Google form! No voltage flows. And by the way, I just told you how to do this, if you were listening, in the previous example. Can you take that knowledge and apply? Google form what? L? Oh, I can't. Letters. Find V here. I will emphasize one more time that no current is flowing in this circuit. No current is flowing in this circuit. Nope, you're all missing it. All but like 2 of you. Okay, what does Ver tell us? If current is 0, what does that tell us? Does that tell us that the voltage is 0 on the resistor? Across the resistor. So if I've got 12 volts on the top of the resistor and V equals 0 in V equals I times R, what's the bottom of the resistor got to be? Listen again. I hear a dead silence. V equals I times R tells how much the voltage changes from one side of the resistor to the other. If I have 12 volts here and I times R is 0, how many volts are left here? 12. If there were 12 volts here and 0 volts here, that would drive a current. If you have a voltage difference across the resistor, that's when current flows. If no current is flowing, this point is 12, this point must also be the same level. If I have a tube full of water and it's open on either end, if I put one side at 12 inches up and the other side at 0 inches up, water will flow through it. Maybe marbles is a better picture to have. If I put the left side at 12 inches and the right side at 12 inches, is there flow? No. So the correct answer to question M is there are 12 volts of voltage here. Almost everybody got K wrong. Let me give you another shot. Question N, which is the letter that comes after M. K again. Tell me what you think now, if you can apply the knowledge that you just gained, apply what I just said. Can you tell me now what you think the voltmeter will read? Again, we have just deduced that the bottom of that 4 ohm resistor is at 12 volt potential. What do you think the voltmeter says? And then what do you think the Fox says? Yes, people are learning things. I love it. Okay, I am muy pleased, very pleased, great. You have correctly deduced that there's 12 volts of voltage here. Oh, and how much can the voltage change across this resistor? If there were a voltage difference across this resistor, would there not be current? There is no current, therefore how much does the voltage change across this resistor? It does not. If I define this point to be at 0 volts, what's the voltage here? 0. If this weren't 0, this point is 0, this is anything but 0, there'd be current flow here. I said the current flow is stopped up by the voltmeter. Therefore, whatever voltage is here is identical to over here. No voltage is burned up in this resistor. There's no pressure across this resistor. So if this point is at 0 volts and this point is at 12 volts, what is the voltmeter feeling? 12 volts. Okay, that involved really 3 steps of reasoning. I want you to turn to each other, and from the top, if I put a voltmeter in series in part of a circuit, what's that going to do and why? Turn to each other and argue. Discuss. Tell each other why. I will give you a practical example that you can argue about. Here, you want to argue with your classmates? There's a practical example you can discuss. See if you can apply your knowledge and figure this out with each other. Number 5, right? Yeah, that's what you wanted? Okay, I think we'll do it. Hey, show me what you got, by the way. Show me what you got. Google question. Oh, what does this volt say? What does say? No current flows through that left branch. What's going to happen? Hmm. Hmm. No. I think you guys are guessing instead of calculating. Hey, so hint for this. No one's got it right yet. Hint for this. If the voltmeter blocks any current from flowing, if this is effectively an open circuit, can you not simply cut this out? Imagine cutting this resistor and voltmeter out. Yeah? Okay, what voltages and currents are there if we've got a 1 ohm in series with 1 ohm? How much voltage will be present at this point if you just had a 1 ohm in series with 1 ohm? Not 2 ohms, not 2 volts. I've got a 1 volt battery. It can't be 2 volts. Current is flowing. How much current flows? Half an amp. 2 ohms, right? 2 ohms, 1 volt, that would be half an amp flows. If half an amp flows through 1 ohm of resistance, how much voltage gets dropped? Half a volt. This point up here has half a volt of voltage left. Does current flow through this resistor? No, no current flows through this resistor. How much does the voltage change from this point to this point? It doesn't. How much voltage is left for the voltmeter? Half a volt. Oh? Oh? No, you're surprised. Work it, baby. Argue it through. You can reason through this. You'll have a much better intuition about how electricity, you'll get other questions right. Again, if nothing flows through that center branch, then you've just got 2 1 ohm resistors in series. 50-50 voltage drop. Question. Wait, say that again? Yes. Current is flowing. So no voltage is burned in this resistor. But do you see that half an amp flows? Half an amp flowing through 1 ohm drops how much? Half a volt is lost. If I start with 1 volt and subtract half a volt, I've got half a volt left, right? The voltage at this point is 1/2. If the voltage is half here and no current is allowed through this resistor because blockage, how much voltage is left? Half. In the previous question? Well, let's look at the previous situation. It's a different circuit. Now the voltmeter is blocking up the only path. There's no current flow whatsoever. This is a complete series circuit. They're different circuits. Absolutely. You have to analyze them differently. Look, different topologies, different analysis. Okay, in the 6 minutes, I've got 6 minutes that remain. Let's hit question 5 on the homework. Or give a hint. On the what? Midterm 1 practice? Where do you want me to be? Homework 4. Oh crap. Homework 4, question 5. Okay, so we're going to talk about this sucker is stuck in place and this sucker can rotate. Tell me this, is this north going to be attracted up or down? Right? North is not attracted to north. North is attracted to south. Which side is this going to be attracted to? Does this want to go up or down? Shoop. Which direction does this have to turn in order to get the north down and the south up? That's clockwise. Well, if it goes the other way, then it's going to be bringing the north first closer to the north. Coming up, then you get north closer to north and then south to south. Now, if you flick this sucker, its inertia can carry it over. You've just invented an electric motor. But no, what if you just release this from rest? This north is going to be pushed away from this. There's a downward outward force here. The south is going to be pulled towards. Exactly. Please, Selena.
Problems that have to do with two different parts.
Selena just asked if there are 2 battery problems. I totally reserve the right to put 2 batteries in series. I won't put 2 batteries in parallel. If you have 2 batteries in series, what happens to the total voltage? They combine. It adds up. If I have an electricity charge that goes through battery that gives me 4 volts and then gives me 6 more volts, I've got 10 volts. There we go. Yep, that's it.
Homework number 3, question 1, it had to do with light bulbs. Will we see anything like that?
Light bulbs are resistors for our purposes. Resistors are light bulbs for our purposes. Okay, we're out of time. I love you. Adios. Good luck on Wednesday. You may. Wait, let me hit stop on the recording.